So, guys, what subject are we doing today?
Nuclear physics from physics,
Okay,
obviously. Yeah,
nice.
nice. Okay, I think we can start. Sairam, are you recording? Okay, then let's get into it. So, is everybody able to hear me
Yeah, your voice
correctly?
is clear.
Okay. Can everybody see my screen? Is my screen visible? Okay, yeah. Yeah, okay. So, this is the basics. You just need to know that an atom consists of a nucleus in the middle with protons and neutrons and electrons revolving around it. That's it for the starting things. Then I think we can go on to the alpha particle scattering experiment where Ernest Rutherford, this random scientist guy, shot alpha particles into a thin piece of gold foil and noted some observations. He noted three important things from which we can deduce some conclusions. So, first, most alpha particles just simply passed straight through without any deflection. So, what can we say from that? So, an atom mostly consists of empty space because nothing happened. Then, some alpha particles were deflected at small angles. And from this, we can say the nucleus is small, dense, and contains most of the mass of an atom. Why? Wait. Oh, wait a minute. Oh, then he also observed that very few alpha particles deflected at large angles, or maybe did a 180. And why would an alpha particle deflect? So you need to know an alpha particle is positively charged. So obviously, uh, same charges repel. And so we can conclude that the nucleus is also positively charged. And so those are the three conclusions and observations that he made. Then you need to know that atoms may form positive ions and negative ions by losing or gaining electrons. Then is one of my favorite topics, nuclear fission. And nuclear fusion. These two are very important. There's going to be a bunch of questions being asked from them. So let's go over the definitions of each of these. A nuclear fission is when a large nuclei split, usually by the means of a neutron, splits into two lighter nuclei. Um, you also have to know nuclear fusion, which is, wait a minute.
Is something wrong?
I was muted. Uh, Justin. It was my sister, bro. I'm sorry.
Don't worry about it.
Of course. Mhm. So nuclear fusion is the joining together of two lighter nuclei, two or more lighter nuclei form a larger nuclei. And does anybody know where nuclear fusion happens?
Nuclear fusion
Yeah,
in the stars and some laboratory in US and
exactly.
other countries.
So, well, I didn't know about the laboratory in the US, but in stars, yes. Nuclear fusion happens in the stars. What it does is really important. It joins together two hydrogen nuclei to form helium, and this releases heat and all of that whatnot.
I had a question for you.
Yeah,
So the hydrogen comes together to form a helium, right? So the helium
yeah.
that is formed, is it a isotope of the normal helium or like the actual normal stable helium? Which one is it?
Yeah. Let's see. I have no idea. Well, I know. I feel like it's going to be a stable nuclear helium, Do you
So
know?
it should be a stable one, right? So
Yeah,
two,
because two hydrogen. Yeah.
yes. Let me just look it up.
Yeah, it's stable helium, definitely. Right?
It says both stable and isotopes, depending on whether normal hydrogens are fusing or isotope of hydrogen are fusing together.
Yeah, okay. That makes sense.
Yes,
Okay, let's go on to the next topic, which is the relative charges and masses of protons, electrons, and neutrons. So let's start with the charge. A proton has a relative charge of +1. Its real charge is much lower and it's different from the relative charge. It's relative to an electron, it has a charge of +1. An electron has a charge of -1. And a neutron has a charge of 0. And I want you guys to remember this. It's really important later on as to radioactive decay and whatnot. What's the charge? Let's go on to the mass. The relative mass of a proton is 1. The relative mass of an electron is 1 in 8,000, yeah, 1,824 or something. It's usually just negligible. You don't really take the mass of an electron into account. The mass of a neutron is also 1. Then let's go on to the nuclide notation, which is A and Z. This is how we can show the amount of protons, neutrons, and electrons of an atom. First, let's talk about the mass number or nucleon number. It is basically the amount of relative mass compared to a carbon 14 atom has. And it usually is the combination of the amount of protons and neutrons. It always is. This is the proton number or atomic number. It denotes the amount of protons and or slash electrons a atom has. Then how do you find a how do you find the amount of neutrons since it's not explicitly stated? You do A minus Z. You subtract Z from A. Remember that some questions do ask you to explain how you got the answer. Some questions directly ask you to get to the answer. Then we have isotopes. What is an isotope? An isotope is an atom. An isotope is an atom of the same element, but a different number of and the same number of protons. It is the atom of the same element because the proton number actually dictates what element an atom is. So it has to be the same amount of protons, or it would be a completely different element. And we don't want that, do we? You also need to know that the proton number shows the relative charge of a nucleus. So we're only saying this nucleus has this charge because neutrons obviously have no charge and protons have this set charge. So the proton number is the charge of that nucleus, just that nucleus, not the entire atom. The entire atom is usually neutral unless it's an ion. Then we need to know what background radiation is. Background radiation is the radiation that exists all around us. Let's go over a few sources of background radiation. We have radon gas in the air, cosmic rays from the sun, which is radioactive, then rocks and buildings. That was really interesting. How could rocks and buildings emit radiation? Yeah, that was introspective. Then food and drinks as well. So you need to remember these four as you might be asked for natural sources of background radiation, and these could be explained. So we know that radiation exists all around us, but how do we measure this radiation? 1 second. We measure it using a detector. This is the detector connected to a counter. This counts the amount of radiation per second. It's usually in seconds. Count rate is usually measured in counts per seconds or counts per minute. So then we need to know about the emission of radiation. So why is radiation emitted? It's it's usually because the nucleus has an excess of neutrons. That's more than necessary. Usually, it's more stable when the amount of protons is equal to the amount of neutrons. But when it has an excess of neutrons, it wants a way to emit that neutron, get rid of it, so it can achieve the stable state. Just like we are trying to achieve stability in life, an atom tries to do the same. But also, we need to know the property of radioactive decay. It's it's spontaneous, which means it's instantaneous. It happens instantly, and random, which means we don't know when it's going to happen at all. So, what are the types of decay? There are three types of decay you need to know. It is alpha, beta, and gamma. Each of these has specific properties, which we are going to discuss. But first, let's think about radioactive decay. Radioactive decay can emit these three particles, as I said, and during alpha and beta decay, the nucleus changes to a different element. Why is this? A helium 2,4 atom is released during alpha decay. So the proton number changes, and the amount of proton changes means the atom changes and it forms a different element. The same thing with beta. And why is this? You don't need to know about positrons, but what happens is a neutron is broken down into a proton and electron. So its proton number increases, so it becomes a different element. So as we know, beta is a electron. Beta particles can be described as a electron. You need to know that questions do ask this exact thing. So isotopes of an element may also be radioactive due to the nucleus being too heavy, not just because of an excess of neutrons. It just maybe it's too heavy and it doesn't want to carry all that weight. What else do we need to know? Yes, like I said, we need to know about the nature of beta emissions, alpha emissions, beta emissions, and gamma emissions. So first, alpha particles have the most ionizing effects. They are the most ionizing. What is ionizing in the first place? Ionizing is when an electron is knocked off, or basically the particle loses or gains an electron. That's it. And so it's the most ionizing. But also, it doesn't have much of a range. It can only go for a few centimeters, and then that's it. That's all it can do. That's why nature balances itself. Next, beta particles. They are less ionizing than beta relative to gamma. I mean, alpha. Beta particles are less ionizing, but they have a further range. They can go further, and you also need to know what they can pass through, what they can be stopped by. A alpha particle can be easily stopped by a thin sheet of paper, whereas for a beta particle, you need a few centimeters of aluminium, or you can say thin sheet of aluminium. And next we have gamma rays. Gamma rays, gamma ray is part of the electromagnetic spectrum, and it's not really ionizing at all. It's very limited in its ionizing ability, but it has the furthest range. Nature balancing itself. Isn't that interesting? It can go the furthest. It has a range of several kilometers or just forever. It's a electromagnetic ray, but this can be stopped by a thick block of lead, or uh, some people say several centimeters of lead. Both are fine. It's all good. We also need to know their penetrating abilities, which is this. And you also need to know their kinetic energy and electric charge. Alpha particles have the most kinetic energy. Beta are always in the middle of the pack, and the gamma has the least kinetic energy. Now that you know what the effects of these are, let's talk about a few bad sides of radioactive decay. So this can cause cell death, basically the death of cells. That's it. Mutations if your DNA is affected, or cancer. So that's why we always limit ourselves to radiation that we receive. Some precautions that we can do are reducing exposure time, limiting the time, like I said, limiting the time we have in exposure to any radioactive substance. Just run away from it. Do not go near for too long. You can also increase the distance between the source and yourself. So let's say this is the source. You want to be as far away from it as possible. You need to reduce exposure time. You need to increase the distance between the source and you. And there's this thing called as shielding. You can use shielding to absorb radiation. So let's say you get a big shield with lead, and so that no radiation can really pass through it and affect you at all. And you might be thinking, how do you move these radioactive things? Isn't it hard? Do you just use robots? No.
Excuse me.
Yeah.
Can I say something?
Yeah.
Last night I was doing a past paper. There was a question like, you are moving a piece of radioactive substance. Which amongst these precaution do you take? It was a paper two, and the options, I don't remember two of the options, but the relevant ones were, it emits alpha particle, that was stated. You either use gloves or tongs to move it.
Yeah. Yeah.
Which one do you use?
I
Because
believe.
alpha particles are stopped by, as you said, thin sheets of paper. So my thought was, why go the long way of using tongs? Why not just use gloves? But the second point you stated, that we have to keep our distance from the radioactive substance, that was used. That I have to keep distance from the source using tongs. So these sort of things we have to consider, right?
Exactly. All of these have to be considered. But what the syllabus states in this regard is to use lead lined boxes. Did you see that as an option? Oh, I guess. Like you said, we do have to use gloves, which are made from lead, I think. I didn't really see it, but you have to use gloves which are made from lead, or you have to store it in a box which has lead in it, which is lined with lead. So that no matter what radiation is, let it be alpha, beta, or gamma, it cannot escape, it cannot ionize you and cause some bad things to happen. The last topic is half-life. So, what is half-life? Although, indeed, radioactive decay is spontaneous, and random, scientists notice that it takes a certain amount of time for half of the particular isotope to decay, and the same amount of time for the next half to decay, and so on until it becomes nothingness. So, what is the? How do we define this? We define this as half life as the amount time taken the nuclei in a particular decay. We have to use this in past papers where they might we need to use this in papers where they might give you a graph, and from that they might ask you to deduce the half-life, or they might give you the half-life and ask you to deduce the value of that isotope. And if you're taking core, you will not be asked to calculate with background radiation, but in extended, you do have to calculate with background radiation. So in a graph, when it goes constant, when the radiation emitted does not decrease anymore, you can take that as the background radiation. And what you have to do when calculating the half life or the count rate, you have to subtract it first and then calculate it later. So I think that is most of what we have to do. The thing remaining is we have to explain how the type of radiation emitted and half life determine which isotope is used for some applications. So let's say you don't really need to know the nitty gritty and how this exactly works. So let's say we have a smoke alarm. Do we need a isotope with a large half-life which doesn't decay as fast and lasts for a really long time, or something that quickly decays and doesn't really do anything much? Anybody?
Long half life, I guess, so that we don't have to change it frequently.
Yeah, exactly. Exact reason. Uh, and that is most of what, that's all of it, I think. And excuse me if this class wasn't as good. It's my first time ever doing something like this. I am trying to improve, so thank you for attending. It has really helped me. If it has helped you, it's amazing. It's great. Thank you for joining, and
Yo, is it
we'll see you
over?
later. Yeah,
Uh, Yo, I just joined now. Is it like really over?
yeah.
Oh, all right. Thanks. All right. And yeah, this is my voice, by the way, if you're like
Hey,
wondering how I
Bayazid, what's
sound.
up? Yeah. I am pretty sure we might have missed some things, but I did cover most. Yeah, most of the things in the syllabus. And